Hello, everyone, and thanks again for being here during our seminar. For today's presentation, we have a presentation titled Effects of Triaxial Test and Strain on Multiphase Flow in 3D Printed Fracture Sandstone Analogues. So before we begin, please keep in mind that there is a list with the attendance. Please be sure that you sign on that in the most clear way. So today's presentation, our abstract is this. Hydrocarbon reservoirs are dynamic systems that change considerably through their life cycle. As primary hydrocarbon production decreases reservoir pore pressure, the in-situ stress state is modified, leading to an increase in the effective stress. This change results in the deformation of the reservoir rock mass, which influence the flow properties of both the intact rock and its fractures. Such stress dependency are especially evident in the alteration of multi-phase flow properties of the rock, namely relative permeability and capillary pressure. These alterations affect the balance between viscous and capillary forces governing fluid exchange between the rock matrix and its fracture, thus impacting the reservoir flow physics. This study investigates the effect of stresses and strain, both normal and shear, on drainage relative permeability, drainage capillary pressure, and matrix to fracture flow contribution in sandstone analogues produced using 3D printing technology. These analogues, featuring both intact and fractured components, are designed to simulate fractured reservoir rocks. The experimental results contribute to the assessment of realistic hydrocarbon recovery, considering the stress sensitivity of naturally fractured reservoirs during depletion. The stress path sensitivity of multi-flow is in fractured porous media significantly affect the performance of hydrocarbon recovery, geothermal processes, radioactive waste repositories, and capture carbon and storage operation. For this presentation, we have with us Angel Sanchez Barra. He is a PhD candidate under the supervision of the dear Dr. Rick Chalaturni and the dear Dr. Gonzalo Zambrano at the University of Alberta. He holds an MSc in petroleum engineering from the National Autonomous University of Mexico. Angel's research is centered on reservoir geomechanics with a keen focus on stress-dependent multi-phase flow in fractures and fractured porous media. He also explores the application of 3D printing technology in geosciences. Before joining the University of Alberta for his PhD, Angel worked as a field engineer at Hydrocarbon. So please join me welcoming Angel.
Everyone, good afternoon. First of all, thank you all for attending. It's great to be here. Also like to thank my supervisor and my co-supervisor, Dr. Rick and Dr. Gonzalo, and special thanks to all the GRF team here, and especially Nathan Baseman, who has been very supportive through this process. And so with that, I will talk about my doctoral studies, my research, which is the effects of triaxial stress and strain on multiphase flow in 3D printed fracture sandstone analogues. Just a second. Okay, thank you, Daniel. So here's the outline of the presentation. I will start with a brief introduction of my research. I will follow with some literature review and what we have done over the past decades. I will show my hypothesis my research objectives, and then I will explain my methodology and go through some of the results that I have. And at the end, I will give some conclusions. So we'll start with the introduction. So as Daniel said in the introduction, so hydrocarbon reservoirs are dynamic systems that undergo significant changes through their life cycle. The reservoir rock deforms in response to variations in defective stress, particularly during production and stimulation operations. And what it basically means is that, so like the goal here is to try to extract hydrocarbons from reservoirs. We can do either conventional reservoirs with naturally fractured properties or doing hydraulically fractured rocks. But at the end, we have these rock structure composed of intact parts and fractures, and they both have some properties. So when we start extracting hydrocarbons, we are basically removing the pore fluid that is the support, and we're inducing some effective stress, and this will change the properties of the media. Just in the schematic here, when we reduce the pore pressure, the effective stress increased because the total stress is kept almost constant, the proportion is constant, and the horizontal stress may decrease slightly. So over the past decades, people have studied these behaviors mainly in fractures only and in porous media. And so I think a best way, like a nice way to put it is like to try to understand what is the effect of stress. But so we consider the state of stress. We have a shear component and a normal stress component of the state of stress, right? The shear component would induce some shear failure, and the normal stress would induce volume change. So over the past decades, people have studied this. For example, we start with the simple, which is the single phase flow. We have like an intact rock, and then we see like a lot of people have been conducting experiments on how the permeability is affected by this deformation, etc. If we go to the fracture sites, a lot of people as well have been playing with single phase flow, changing the fracture thickness, things like that, and seeing how it behaves. But when we go to the multi-phase flow, it's a bit more tricky because only until recently, people have studied the relative permeability, how they change with respect to the increase in effective stress. And the shear stress also only normal stress, but there's no information about the effect of shear stress on fractures or fractured media. Specifically, there's no information about fractured porous media, which is different because the matrix also contributing to flow. So my hypothesis is that the primary hydrocarbon production leads to reservoir depletion, inducing geomechanical processes such as changes in effective stress. So these mechanisms induce normal and shear stresses that change the drainage, multi-phase flow properties like the relative permeability and the capillary pressure, and therefore affecting hydrocarbon recovery. So I think the focus here is because like typically in the industry, they're not considering that these properties are being changing over time. And these are dynamic properties, which means they're always changing. We need to quantify that. So the simulators don't account for this. So I think it's really important to understand. So if we take, for example, a fractured media and an intact media, it's just in a schematic based on the literature, but basically we'll see like something like capillary pressure really low, almost nothing. The relative permeability, the range saturation, also a small range. In terms of the intact, we'll see like the typical capillary pressure curve and then the multi-phase flow. So what would happen? So when we increase the isotropic compression, we're basically compressing the fractured porous media, and these properties are changing. So for the capillary pressure typically goes up, and like sometimes like for the fractures you don't even see it, but it all depends on the interaction of the fracture. And so the curves, the relative permeability curves typically shift to the left in some of the cases because we're compressing and we're having more interaction with the saturation of the rock. If we go to the shear, and this is a bit more tricky, and we don't know to this point, but it's a bit tricky because we don't know if the rock will dilate, will contract, and many things can change, and it's a bit more tricky. So my objectives are the following. So the primary ones, we want to quantify the effect of shear and normal stress on drainage, relative permeability, drainage capillary pressure, and especially the mass transfer between the matrix and the fracture. For this, we need to design and build an experimental system that allows us to measure multi-phase flow properties under triaxial conditions. We also need to fabricate 3D-printed reservoir Sandstone analogues. The secondary objective, and not to work with this, we need to analyze the variability and repeatability of the 3D-printed samples, develop densification and approach for and porosity permeability reduction to customize these rocks the way we need it. We need laboratory testing using the 3D printed sandstones with intact parts and with fractures in order to obtain the stress-dependent drainage relative permeability, drainage capillary pressure, the hydraulic aperture, and matrix of fracture transfer functions. And with this, we can assess the impact of the mechanical processes on the recovery mechanisms of naturally fractured reservoirs using a case study in the Gulf of Mexico, a CalKL. We're proposing an integrated approach to characterize this impact and show what are the governing processes here. So to do this, so we basically have three main steps. The first one was to try to understand first the physics of the reservoir, looking at the rock, if it's the fracture, what is the porosity, things like that. Look at the fluid properties, and then so the idea was to try to replicate some sort of like proxy physical model that we can use to run experiments. And obviously these have its own challenges, but we can explain them in this process. And then at the end, trying to build this system that allows us to measure these properties with these analogs and try to understand what happened. So we'll show some of the results. First, I'd like to briefly describe the reservoir. So this reservoir, it's located in the Gulf of Mexico. It was the most important reservoir in Mexico. And for example, just to put in context, the orange line here, it was the oil production in Mexico. And then, so this pink one, it's the production from this reservoir. So in 2005, let's say like the production of oil in Mexico was around 3.5 million barrels per day, and this reservoir itself was 2. So it was like 2/3 of the production. So it was very important. And so then the production started decreasing, and you need to like compensate that with other reservoirs. But this is really important. So the overview of the reservoir, porosity of the rock, it was around 10 to 12% of the matrix part. The permeability of the insect or the matrix was around between 5 and 100 millidarcies, and the fracture was between 1 and 5 darcy. The thickness of the reservoir was between 100 and 300 meters at a depth of 2,500 meters through vertical depth. The temperature of the reservoir was an average of 100 degrees. So if we look at this, this is from like top view, we can see like this is a huge reservoir. And so in order to quantify, we need to like focus in one specific area. And so that's why we select this small block in the northwest region of the reservoir. And the nice thing about this is that it is isolated from the rest of the field. So whatever happens by some faults, so whatever happens in the big reservoir is not affecting this part, and vice versa. So here we have a simple flow model of the reservoir, just to show like how the pressure it's reducing over these 20 years. And we see, so the color means the intensity of the pressure. I think I didn't put legend, but it's also just to show how the pressure it's reducing, and therefore we assume that the effective stress is increasing. Now, so I'll explain about the 3D printed rocks. So in order to try to have a proxy model or something we can use to run these experiments, we need something that we can do multiple samples. Yeah, so we chose this method. It's binder jet additive manufacturing. It's a rapid manufacturing process. There's high repeatability and homogeneous properties, at least with respect to real rock. It's cost effective. We can print like almost like 15 or more samples at a time. We can customize the fracture, the geometries, specifically the fractures. And I think this is one of the most attractive parts. So we want to replicate a fracture. I think there's no other better method than 3D printing technology, just because you can try mold, you can try something else. But if you want to do like what you want to do, like 15 samples with the same fracture, good luck if you want to use something else. So that's why we choose this method. And obviously we also try to modify the porosity and permeability and things like that. So this process is basically, so this binder jetting thing is a layer by layer thing, where so sand has been deposited on a box, and then it's spread evenly and a smooth bed. And then the binder, it's been injecting it's like a glue with a 2D shape of the object, layer by layer until we construct the final part. So once we have like these 3D printed part, we thought like, okay, let's look at the properties. If we want to print, I don't know, 40 or something like that, many samples in one print job, can we actually replicate the properties? And the answer, it was no. So like if like we print many layers, for example, this would be like the box of the printer. So if we put like many samples and we start printing them, so they're showing actually different mechanical properties. If we plot like the Young's modulus versus the UZS, we can see like a big scatter in the data, so this big spread. So in order to do this, we try to quantify like, or at least find the spots where we have like the best repeatability of the samples, and we select these center of the job box in order to do this. So we published this data a couple of months ago. And also, yeah, we try to look at the standard deviation. So we also try to densify the rocks by increasing the density, the bulk density of the rock through some processes like compaction. So in this method, we apply mechanical compaction to the rock by using some rollers that are like trying to compact the sand layers as you print. And also we try to change the sand mixtures in order to reduce the pore space and get some properties more that fit better for us in this reservoir, right? So we had like a good progress in terms of mechanical properties, but we didn't manage to reduce porosity and permeability. And so that's why we implement something else. So once we have the rock already, so yeah, with the default properties, so we inject sodium silicate into the pore network of the rock in order to try to plot all the pore space, all the network in order to reduce porosity and permeability. So the initial rock with the default properties shows a porosity of around 40% and 1,000 millidarcies. And you can see this graph is the pore network of the rock. So after, like, and this you can plot it here, right? So after we do this treatment, we inject sodium silicate and we try to occupy all this space. We reduce porosity and permeability. So porosity is reduced by almost 50%, and permeability is reduced from 1,000 to 150 millidarcies, which was what we needed in order to create this difference between the intact or the matrix component and the fracture. So we look at the of the matrix here. This is the original matrix. Then we inject the sodium silicate, and then if we zoom in, we can see that the sodium silicate is occupying the previous empty space. So once we have these rocks, and sorry to say that, but until this point is where we start calling the rocks or these 3D printed rocks as rock analogues, reservoir rock analogues, because so far they have at least the flow properties that we need in order to quantify the effects in this type of rock, reservoir rock. So in order to do this, we design and build, and thank you to the URF team for designing and build this system. And so we build this system and in order to measure all these multi-phase flow properties under triaxial and isotropic considerations. So this system has like 5 main components. It have like a triaxial high pressure cell, a loading system. You can see here the flow diagram, the multi-phase pore pressure circuit, and the fluid separation system, and everything. We have many sensors all in place in order to capture pressure, temperature, et cetera, et cetera. So we publish these data as well in Norma. So just to show the main components of the system. So this is a view from the inside of the system. Everything is inside an oven in order to maintain the appropriate isothermal conditions. So we have, like, for example, these 3 fancy pumps in order to inject 2 different fluid phases into the sample, and then we have another one to maintain a back pressure we want, not to replicate the pore pressure that we need. And then so this Triaxial high pressure cell allows us to put a specimen inside the rock, and then we can change independently the axial stress and the radial stress, which is great. And then the phase separation system, I think this part is my favorite part. This allows us to measure the saturation of the rock in real time. And I think this is the biggest differences with respect to other systems where you can do only during steady state periods and things like that, using mass balance yeah, mass balance and things like that. The other, like the only better thing I would say, it's this, just put in a CT scan, but obviously the price would be like way higher. And so for this, so once we have the rocks, when we have the system, we start looking at the main properties, the porosity-permeability relationship, the relative permeability, and some of the mechanical properties, in order to see if we actually manage to have something that we can use to replicate and try to understand these measurements, right? And so we see like the blue dots here represent this data from the 3D printed samples. And we can see that they actually follow a moderate trend from a reservoir in terms of porosity and permeability. So the porosity that we needed, it was something around here, but also this is from intact rocks, which means that it's lower because it's not considering the fracture size. And just the relative permeability, we can see all these black curves that represent the relative permeability of the rock. And we can see like that the blue ones actually match the behavior. And so that's what we needed. In terms of the volumetric strain, bulk compressibility, or rocks are like between 4 and 5 times more compressible than a real rock. But this is actually a good thing, because this allows us to measure the properties that we need in terms of like deformation in a more friendly way. So in order to deform the rock 2.5%, we don't need to like 50 MPa of isotropic compression. So that's good. So once we have this, we select 4 case scenarios where we can use to study the isotropic compression or normal stress in intact materials and fracture materials, and also shear stress. So for the presentation, I'm only going to show these two. And so I will start by looking into this. But first of all, one of the main things in fractures, and we want to implement something straightforward, something simple, is the cubic law. The cubic law comes from Navier-Stokes equations, and if we start deriving the Navier-Stokes equations, we start removing some components, the steady state, the transient component, things like that, the body force. We come up with a very simple cubic law that allows us to measure fluids through parallel fracture with a smooth surface. And so we wanted to use this method because we want to understand the basics of these rocks. And so if we look at the fracture surface of the rock, we scan this fracture with a profilometer. We measured that the surface actually was very smooth. The variation was between 100 microns, so it was good. So in terms of the delta PQ, the pressure drop versus Q in this core fluting in this core fluting test for these rocks, they show a linear behavior, which was a requirement for using the cubic law. And so now we're gonna explain a bit of the effect of normal stress on porosity and permeability for this fracture media. For the matrix part, we can see a decrease in porosity, and also the permeability initially is around 150 millidarcies, and it decreased all the way to around 40. So we have more scatter, obviously at less effective stresses, but we increase effective stress, we have less scattered, and we can use this. In terms of the fracture, so the hydraulic aperture also started around 0.2 and it decreased around 0.9 millimeters. So the permeability of the fracture with respect to the matrix, and this is one of the parts we really wanted to have. So initially the rock was, the permeability was really high. So by doing all these treatments and all that, we can actually have a different behavior of the fracture in the matrix. And so in this case, the fracture controls at the beginning of low effective stresses controls around 95% of the flow. So it's going to be determined by fracture flow. So we start increasing the effective stress. We have like 85% dominated by the fracture. And so that's what we needed. So now these same effects, but now under 2 phases, looking at the drainage relative permeability. So for this case, we only are interested in 2 points. One would be when we have a deformation close to 1, and the other one when we have a deformation close to 2.5. And during these points, for example, at this step, we put some isotropic compression, and then we start measuring the 2-phase flow. So for the matrix, we can see this relative permeability, also for the fracture. So what happens when we increase the effective stress? So what happens is that, and this is confirmation to our hypothesis, the curves are shifting to the left. And so the reason is because when we are compressing the media, either the fracture or the matrix, we're actually reducing the space for flow. So one thing I forgot to mention, like these relative permeability curves are measured with canola oil or oil and nitrogen gas. And so the wetting phase is gonna be the oil, and the non-wetting phase is gonna be the gas, right? And so it's always harder for the non-wetting phase to flow through the rock. So when we start compressing and we start reducing the pore space, we're doing constant flow rate. So the pressure will build up, if you can see here at the bottom. And this increasing in pore pressure will try to invade parts of the rock and try to displace more oil from this process. So the capillary pressure was measured using the porous plate method, which is a variation of the permeable plate method introduced by Hasler and Brenner. So basically, so I need to say, like, all these tests were run, for example, for the same rock, and we resaturate and we conduct the test again. So we actually, it was like a continuous methodology. So it was easy to implement once we obviously figure everything out. But this allows us to measure like many tests in a considerable time. So basically we had this rock saturated with oil, and then we start injecting gas. So once the gas displays everything it can, we have like this steady state where we're only flowing gas. So at this point, the difference between the injection pressure and the outlet pressure is going to be or capillary pressure when the wetting phase is immobile. So it's basically not moving. And so once we have this point, we start increasing the flow rate in order to induce high capillary pressures and reducing the wetting saturation of the rock. So these are some examples of these measurements. So this like the capillary pressure was low for the matrix, and it was even lower for the fracture, almost nothing, to be honest. And this cross is showing the fracture side. So the nice thing about this method is we can actually track what happens with the saturation at all times. So basically, we have the rock completely saturated, for example, here, and then we start injecting gas, and then we start displacing trying to remove all the oil. And so once the gas managed to overcome and flow through the rock, it starts displacing all the oil, and we start recovering everything. So, and the saturation looks like this until we get to a steady state. And when we get to a steady state, we take the first steady state measurement, which was like probably this point. Now, if we increase the effective stress, also confirms our hypothesis. So we're actually crushing or reducing the pore space, making it harder for it to flow. And so therefore, you will need to overcome a higher breakthrough pressure in order to displace the wetting phase. And at the end, same thing, get to a steady state and get this first point. Now, in terms of the shear stress, on the absolute permeability, we also start from one point. So we induce isotropic compression until one point, and then from that moment we start changing the axial stress. So the first point it was like this. So then the second one, higher axial deformation, and the third one. So in theory, in the second point we cross the crack initiation level threshold, and we know because we run several triaxial experiments in order to determine these points. Yeah, and so the third one also, we're almost as well like close to the crack damage, probably past the crack damage. But the permeability, the absolute permeability didn't show this behavior. We would expect to have an increase in absolute permeability when this happened, but we didn't see it. Now, in the two-phase flow, the drainage relative permeability was a bit more interesting because, so same thing. So we start running the first test right here. And then when we increase the axial stress, that's the interesting part. So we did actually see like the evidence of a small fracture. And we know this because we had less interaction with the wetting phase of the rock, with saturation of the rock. So basically, hypothetically, when we induce the axial stress, the non-wetting phase, the gas, flow through some channel and had less or embayed less and recovered less. So when we increase to the next level, it seems like, according to Diaz, it seems like that if a fracture was formed, it closed a bit, and then we managed to again displace a bit more oil. Obviously, we didn't see it when we took the sample out, because it was just like bulging and it was not actually anything visible. This is just to show the difference between the shear and normal defects. So yeah, so for the capillary pressure as well. So the first point, first and second point, almost the same, and because the non-weighting phase is trying to flow through these media very easy. So the third point, when we induce axial stress, we start like closing everything, and the capillary pressure increase, but just slightly. So this may look like a lot, but it's actually like 10 kPa. So it's really low, and there's certain uncertainties because it was so low that our measurements might be like almost fall into a range of errors. So why is this important? So when we look at the effects of shear normal, for example, let's say we start with shear. So we start shearing the rock, and in terms of the recovery, if a fracture is formed, we're actually recovering less. In these experimental cases, we recover between 3.5 and 8.3 less oil from these fracture media. If we go to the normal stress, isotropic compression, we actually increase like 13% of additional oil by compressing the media and trying to displace. So why is important? So for example, so if we found with these findings, if we think about the reservoir, and so for example, these are actual production data from the reservoir. This is the production data. The red one, it's the production of gas. And this continuous green one is the oil recovery. So we think about this. So I forgot to mention that in this reservoir, like in the big reservoir, the common thing was to inject nitrogen as a EOR technique. They would just inject the nitrogen in order to recover more. But they like this reservoir is kind of old, like the big reservoir is like probably start producing in the early 80s or something like that. And so when they start doing this, and then every new discovery close to that area, they start injecting nitrogen. And so what happened here is that it seems like from these data that they start right away, they start producing from this block or this reservoir, and they will start injecting nitrogen. So, but it seemed like the nitrogen was percolating through the media, and just like they were recovering the nitrogen. So by understanding this, I think it's important because hypothetically, and I don't have actually simulation data or field data to back this statement, but we believe that this could potentially give you the enough information to say, okay, let's not inject nitrogen right away. Let's allow the effective stress to increase in order to have more engagement with the fracture media. And this hypothetically could mean around 13% more oil production, which means by looking at these numbers, it would be around 300,000 barrels, which at today's price would be like $26 million. So my conclusions. So the stress and the strain changes in fracture porous media affect drainage, relative permeability, capillary pressure, and matrix of fracture mass transfers. The evolution of the stress path induces different changes in these multiphase flow properties. An increasing effective stress normal to the fracture aperture induced higher oil recovery under drainage mechanisms. A laboratory testing facility was designed and built to investigate the effects of triaxial stress on multiphase flow properties. Binder jet additive manufacturing was implemented successfully to fabricate reservoir sandstone analogues. The contributions to the reservoir alkali and to the industry in general is that we managed to see these alterations of the relative permeability and capillary pressure and how they're associated with the formation of the reservoir rock. And also we found the optimal conditions under which multiphase flow properties will allow us to recover an additional oil and displace more oil from the matrix through the fractures. And with that, some of the deliverables, some papers that we just published, and some more collaborations. And I think that will be all. Thank you. If you have any questions.
Thank you very much. Okay, so now we have our Q&A session. So if anyone has a question, please raise your hand and I will go with the mic. Yep. What?
I can just speak up from here.
I don't think, yeah, but it could be a report. Oh, during the video, you know.
Hello. Did you do any coupling model analysis with thermomechanical gradient?
No,
Temperature was kept.
no, to be honest, it was a bit out of the scope. Initially, I wanted to do some coupling work, but to be honest, it was a lot. I wouldn't rather it soon if I go to that direction. I do want to at least do a bit of flow simulation. So we have the flow model, and we want you to at least try to capture these changes in the relative permeability and see how this is affecting the recovery. It's not going to be the complete behavior because we're not changing the mechanical properties, but at least I think it will give you an idea or a starting point to look into these effects at the reservoir scale, because obviously it's different, right?
Anybody else?
So you talked about the printing sample. You kind of modify the porosity by injecting silica.
Yeah, sodium silicate.
So
Sodium silicate.
can you talk a little bit about what's the process?
Yeah, so this process, we basically we inject sodium silicate under like vacuum. So we put the samples under vacuum, then we start injecting sodium silicate. Sodium silicate, it was nice when it was selected because in theory it was gonna be, it was wetting the grains nicely because they're from silica as well. And so the idea is like once we inject the sodium silicate, we can that's liquid, right? Like that's liquid, it's dissolved in water. So we do this and then we inject CO2. I didn't have enough time to cover this method, but we inject CO2, and then when the CO2 interacts with the sodium silicate and the water, it forms, I think it forms carbonic acid, if I'm not mistaken. And then so there's like some reaction which generates silica gel, and also generates, I think, our sodium carbonate, something like that. And then a bit of water. So we extract the water with heat, and then at the end we end up with something like it's not completely, like it's not a very like solid, it's not really strong, but at least it's something that allows us to reduce porosity permeability. It's not adding any mechanical properties. Actually, I believe with these results that it actually may affect the mechanical properties slightly, because when we inject the CO2, it may put a bit of tension between the grains. But that's okay because the goal was about reducing the flow properties, and that was the case. I think in the future will be a better way to explore something else that allows you to do both flow and mechanical properties.
Another question? Slide. Regarding the porosity change. So
yeah,
there is a decrease in the porosity change, but it's not substantial, that decrease. We know that those kind of materials is really compressible.
Mhm.
Like could you elaborate that? Because I would expect for an increase in effective stress of almost 16 megapascal, a really huge decrease in the porosity due to the huge compressibility of the rock. Any idea why that decrease is too small?
I think so. Initially, we for example, we saw a behavior in the 3D printed samples that were not treated with anything. So the initial permeability is around 1,000 millidarcies, 1 RC. And so when we increase the effective stress to these levels, we saw a decrease, I think, all the way to 200 millidarcies. In this case, this extra material, like this extra phase, might help a bit in order to maybe not compress as much as sample untreated. But yeah, so this would be the way the permeability is decreasing. When we see the fracture side, it's obviously more compressible and it's affected the permeability a lot.
And such question is that in your conclusions, and it makes sense once we see the final probability, the relative probability is affected by the direction, the relationship between the direction of the stresses that are applied and the direction of the fracture. So when we have a more complex system with multiple fracture families in multiple directions, what do you believe that will be the behavior? Do you believe that it will be covered mainly for one main family of fractures, or it will be something like an average of any other random behavior?
I think it's interesting. I think Sobak was saying, one of the chapters from Sobak, he was mentioning, like, obviously the direction of the fracture has been affected by the stress, but I think you would see more this behavior if you do triaxial stress conditions rather than if you do only isotropic compression. You may see maybe a slight decrease or more decrease in certain fracture apertures rather than others, especially the ones that are normal to the fracture direction. Obviously, if you add like some triaxial stress or some a higher axial stress, it will depend on the direction of the fracture, but also that can affect. And then at this point, it's what I'm saying, like it's a bit tricky because even with simple geometries like this, it's hard to understand because like the fracture. So the thing is that, so if you start inducing effective stress to the fracture, what can happen is that the fracture can close, and that also depends of the fracture surface. If you have a fracture surface that it's has certain roughness, and you start increasing the axial stress, you can either probably close the fracture with the gout that is being produced and all the shear that is producing and breaking all these grains. You can shut down the permeability, or you can also like create this shear failure and create this pad propped with the grains and things like that. And actually, you can amplify the permeability, but it's hard to say, and it's hard to have an exact solution for that. And so I think at least with this, we can understand how this process are affecting the flow and have a better idea. But also depends, yeah, on the type of stress that you're putting to.
Okay, there is a question in the chat. I will read. It says, I just wonder how long did it take to complete a full PC curve, a capillary pressure curve for one of those printed samples using the porous plate method? And did you do or compare any wettability measurement with real data?
So yeah, so for the time, so typically, so this test, for example, with one rock, for the capillary pressure only, it would probably take a week, because a week or a bit more than a week, because we try to ensure that everything is completely saturated. So the rock is completely saturated, so we can then inject the nitrogen with the confidence that everything is saturated, and what we're displacing is what actually was induced by the capillary pressure. In terms of the real data, so I have compared these results with the real data from this reservoir, but it's with the capillary, in terms of the capillary pressure, it's not that simple to compare, mainly because the media that they tested from the reservoir is from intact material only, and it was like the porosity was low. And for my rocks, it was a fracture media, and the intact material by itself, it was not so tight as the reservoir. And also, well, in that case, I think the big difference, and I also think it's very important for these tests, is that so they measure the capillary pressure with mercury, and so what they do is a bit different, because I think they're not capturing the initial part, the displacement of the wetting phase by the transient part of the flow injection. But yeah, but definitely it's really interesting.
So Thank you very much, Angel, and thank you very much, everyone, for being here. Wait for you to see you next week. Yeah, that's all.
Thank you all. Thank you very much.